welcome to this problem walkthrough. Today, we will be exploring problem number 612, titled Shortest Distance in a Plane. In this problem, we aim to determine the shortest distance between 2 points based on specific constraints. Stay tuned as we break down the problem, explore potential solutions, and analyze their efficiency. Let's get started. In this problem, we are tasked with finding the shortest distance between any two distinct points in a 2D plane. The points are given as an array where each point is represented by its x and y coordinates. To calculate the distance between 2 points, we use the Euclidean distance formula, which is the square root of the sum of the squared differences between their x and y coordinates. Our goal is to determine the smallest distance among all pairs of points and return this value as a floating point number, rounded to 4 decimal places. The input will be a list of points, and the output will be a single number representing the shortest distance. Let's now explore some examples to better understand the problem. In our first example, the input is a list of points 0, 0, 1, 1, 2, 2, and 3, 3. The task is to find the shortest distance between any two of these points. Among all possible pairs, the closest pair is 0, 0, and 1, 1. Using the Euclidean distance formula, we calculate the distance as the square root of the sum of the squared differences between their x and y coordinates. Specifically, this is the square root of 1 to 0 squared plus 1 to 0 squared, which simplifies to the square root of 2. When rounded to 4 decimal places, the result is 1.4142. This illustrates the process of identifying the closest pair and computing their distance. In our second example, the input points are -1, -1, 4, 4, 7, 7, and 8, 8. After evaluating all possible pairs, the closest pair is found to be 7, 7, and 8, 8. Applying the Euclidean distance formula, we calculate the distance as the square root of 8 to 7 squared plus 8 to 7 squared. This equals the square root of 1 plus 1, which simplifies to the square root of 2. When rounded to 4 decimal places, the distance is again 1.4142. Additionally, consider a third example where the points are 0, 0, 3, 4, and 6, 8. For the third example, the closest pair of points is 0, 0, and 3, 4. Using the Euclidean distance formula, we calculate the distance as the square root of the sum of the squared differences in their x and y coordinates. Specifically, this is the square root of 3 to 0 squared plus 4 to 0 squared. Simplifying further, we get the square root of 9 plus 16, which is the square root of 25. The result is exactly 5.0000 when rounded to 4 decimal places. Now let's consider some constraints and edge cases that are important for solving the problem effectively. The problem comes with several constraints and edge cases that need to be addressed. First, when there are only 2 points, the shortest distance is simply the Euclidean distance between them. Next, if the coordinates are very large, such as -10 to the power of 6 and 10 to the power of 6, the solution must handle these values without causing overflow or precision errors. For points that share the same x or y coordinate, the formula must still calculate the distance accurately. Additionally, with a maximum input size of 10 to the power of 4 points, the solution must be efficient enough to complete within the time limits. Finally, the output must consistently be rounded to 4 decimal places to account for any floating point inaccuracies. These considerations ensure the solution is robust and handles all cases correctly. To solve the problem of finding the shortest distance between points on a plane, the brute force approach is the most straightforward method. Here, we calculate the distance between every possible pair of points using the Euclidean distance formula. Since there are n*(n1/2 unique pairs for n points, we would use 2 nested loops, one to iterate through each point I and the other to iterate through the remaining points j where j greater than I. For each pair, we compute the distance as the square root of the sum of squared differences in their x and y coordinates. Throughout this process, we track the smallest distance encountered. While this method is simple and requires no extra space beyond a variable to store the minimum distance, its time complexity is n squared, because we calculate the distance for all pairs. As a result, it becomes inefficient for larger datasets. Although the brute force approach is easy to implement and works well for small datasets, it quickly becomes impractical as the number of points increases due to its quadratic time complexity. A more efficient strategy involves sorting the points and using a divide-and-conquer approach. The key insight here is that the closest pair of points are likely to be spatially near each other, and we can leverage this property to reduce the number of comparisons. By dividing the plane into smaller regions and analyzing each region separately, we can efficiently narrow down the search space. The points are first sorted by one coordinate, such as x, and then divided into two halves. Additionally, we introduce the concept of a strip region, which is the narrow band around the dividing line. Only points within this strip and with small y-coordinate differences are considered for cross-boundary pairs. This dramatically reduces the number of distance calculations required. The optimized approach begins by sorting the points based on their x-coordinates, which prepares the data for efficient divide-and-conquer processing. After sorting, we recursively divide the points into two halves and compute the shortest distance within each half separately. Once we have the results for both halves, we merge these results by checking the strip region near the dividing line for potential closer pairs that cross the boundary. To ensure efficiency, only points within the strip and whose y-coordinate differences are smaller than the current minimum distance are considered. This method successfully reduces the number of redundant comparisons. In terms of complexity, the sorting step takes n log n, and the recursive checks, combined with the strip comparisons, maintain the overall time complexity at n log n. However, the space complexity is n, due to the storage required for subarrays during recursion. While this approach introduces additional implementation complexity compared to brute force, it is significantly faster for larger datasets. Given the inefficiency of the brute force approach for large inputs, the optimized divide-and-conquer strategy was chosen. This method reduces the computational complexity from n squared to n log n, making it far more suitable for scenarios where performance is critical. The main insight that drove this decision was the realization that the closest pair of points are often located within a small localized region, meaning we can avoid comparing all pairs. By sorting the points and limiting comparisons to a narrow strip, we eliminate many redundant calculations. Alternative methods, such as the grid-based approach, were also considered. While grids can help reduce comparisons, they are more complex to implement and less efficient than the divide-and-conquer method. Ultimately, the sorting-based strategy strikes the right balance between efficiency and implementation complexity, making it the best choice for this problem. To solve this problem, we start by clearly understanding the task. We are given a set of points in a 2D plane, and our goal is to determine the shortest distance between any two of these points. The distance we use is the Euclidean distance, which measures the straight-line distance between 2 points. Mathematically, it can be calculated using the formula, the square root of the sum of the squared differences in their x-coordinates and y-coordinates. Once we understand this, we can approach the problem using a brute force method. Here's how it works. First, we iterate through all possible pairs of points. For each point, we compare it to every other point that comes after it in the list, ensuring we don't repeat calculations for the same pair. Since there are n points, the total number of unique pairs is n times n-1 divided by 2. For each pair, we calculate the Euclidean distance and keep track of the smallest distance we've seen so far. This approach ensures that we consider all possible combinations and don't miss any potential minimum distance. In the brute force algorithm, we maintain a variable, min_distance, initialized to infinity. This variable keeps track of the smallest distance we encounter. As we iterate over each pair of points, we calculate their Euclidean distance using the formula. If this distance is smaller than the current min_distance, we update the variable with the new value. After checking all pairs, the value stored in min_distance will represent the shortest distance between any 2 points. The pseudocode breaks this process into clear steps. We initialize min_distance, loop through all pairs of points, calculate the distance for each pair, update min_distance when a smaller distance is found, and finally return the result. This straightforward approach guarantees that we find the correct answer, as no pair of points is skipped during the iteration. The brute force method works because it systematically evaluates all possible pairs of points, ensuring that no pair is missed. This guarantees correctness, as every possible distance is considered. The Euclidean distance formula itself is derived from the Pythagorean theorem, making it a mathematically sound way to measure the shortest straight-line distance between 2 points. Now, let's analyze the complexity of this approach. The nested loop structure means we compare each point with every other point, leading to a time complexity of n squared. The computation of the distance for each pair is a constant time operation, so the overall time complexity remains n squared. In terms of space complexity, the algorithm uses only a constant amount of extra space for variables like min_distance, resulting in 1 space complexity. There are some edge cases to consider as well. For example, if there's only one point, no distance can be calculated, so this scenario should either produce an error or be explicitly handled. On the other hand, if two or more points are identical, the minimum distance will naturally be 0, which the algorithm handles correctly without any special modifications. The input for this algorithm is represented as a list of tuples, where each tuple contains the x and y coordinates of a point. A list is an appropriate choice because it allows for straightforward iteration and easy access to elements. We use a single variable, min_distance, to store the smallest distance found during the computation. This keeps the algorithm space efficient, as no additional data structures are needed. While the brute force approach is simple and effective for small datasets, there are optimizations to consider. For instance, when the number of points is relatively small, such as less than 10,000, this method is feasible and easy to implement. However, for larger datasets, the n squared time complexity becomes a limitation. In such cases, a more efficient approach, like a divide and conquer algorithm, can reduce the complexity to n log n. That said, the brute force method is still a good starting point for understanding the problem and serves as a baseline for comparison. Its primary limitation is that it becomes computationally expensive as the number of points increases, making it impractical for very large datasets. Here, we start implementing the solution to find the shortest distance between points in a 2D plane using Python. First, we import the math module, which will help us calculate the Euclidean distance between points. Next, we define a class named solution and a method called shortest distance that takes a list of points as input. The first step in this method is to sort the points by their x-coordinates. Sorting is crucial because it allows us to efficiently apply the divide and conquer approach, which we'll use to solve the problem. We then define a helper function, Euclidean_distance, which calculates the distance between 2 points using the formula derived from the Pythagorean theorem. The main logic is implemented in another helper function called closest_pair, which takes two indices, left and right, representing the current range of points under consideration. Within closest_pair, the base case handles scenarios where there are 3 or fewer points. When this happens, we calculate the pairwise distances directly and return the smallest one. This ensures that even small subsets of points are handled correctly. For larger sets, we proceed by dividing the set into two halves. The midpoint is calculated, and we determine the x-coordinate of the middle point. Then, we recursively compute the shortest distances in the left and right halves and store these as d1 and d2. By taking the minimum of these two values, we get the closest pair distance within each half. Now, we move to the conquer step, where we handle the possibility of the closest pair straddling the divide between the two halves. To do this, we create a list called strip, which contains all points within a distance d of the dividing line. Here, d is the minimum distance we calculated from the left and right halves. We include only these points because points farther away cannot form a closer pair. After constructing the strip, we sort these points by their y-coordinates. Sorting by y-coordinate ensures that we can efficiently check potential closer pairs in the next step. Then, for each point in the strip, we check it against the next few points in the sorted order. Specifically, we only compare points that are nearby in the y dimension, as pairs with larger y distances cannot have a smaller Euclidean distance than d. If we find a new pair with a smaller distance, we update d accordingly. Finally, the function returns d, the smallest distance found either within the left and right halves or across the dividing line. To solve the problem for the entire set of points, we call closest_pair with the range covering all points in the input list. This recursive approach ensures an efficient solution to the problem, leveraging both divide and conquer and geometric properties of the points. Here, we start by importing the necessary Java utilities and defining our solution class. The main function, shortest distance, takes a 2D array of points as input. The first step is to sort these points based on their x-coordinates. This helps in dividing the problem into smaller subproblems efficiently. After sorting, there is a helper function, Euclidean distance, which calculates the Euclidean distance between 2 points using the distance formula. This function is critical for comparing distances later on. Next, we define a recursive function, closest pair, which is the core of our divide and conquer approach. Within this function, if the number of points in the current segment is very small, 3 or fewer, we calculate the distances directly using a brute force method. This ensures that we handle small cases efficiently. Then, to divide the problem further, we calculate the midpoint index, which will allow us to split the points into 2 halves for further processing. At this stage, we calculate the x-coordinate of the midpoint, which will help us identify points close to the dividing line. The closest pair function is then called recursively for the left and right halves of the array. This gives us the minimum distances, d1 and d2, for the 2 halves. We then take the smaller of these 2 distances, which we call d. Once we have d, we check for points that might be closer but are split across the left and right halves. To do this, we create a strip list, collecting all points within a distance d from the midpoint line. This ensures we don't miss any potentially closer pairs that span the divide. We then sort this strip by their y-coordinates to prepare for the final, localized comparison. For each point in the strip, we compare it with the next few points in the list, but only if the y distance is less than d. This optimization significantly reduces the number of comparisons needed, ensuring the algorithm remains efficient. If a closer pair is found during this step, we update d with the new minimum distance. Finally, we initiate the recursive process by calling closest pair on the entire array of points, starting from index 0 to the end of the array. This triggers the divide and conquer algorithm we've built, systematically narrowing down the shortest distance between any 2 points in the plane. The function ultimately returns this minimum distance as the result, solving the problem efficiently even for large datasets. By combining sorting, recursion, and optimized pairwise comparisons, this implementation achieves a time complexity of O(n) log n, making it highly scalable for practical use cases. To start solving the problem, we begin with the simplest case where there are only 3 points, 0, 0, 1, 1, and 2, 2. First, we sort these points by their x-coordinates. In this case, the points are already sorted, so the order remains 0, 0, 1, 1, 2, 2. Next, we call the function closest_pair with the indices covering all 3 points. Since there are exactly 3 points, we use the base case to calculate the distances directly. The distance between 0, 0, and 1, 1 is calculated as the square root of the sum of squared differences in x and y coordinates, which gives approximately 1.414. Similarly, the distance between 0, 0, and 2, 2 is approximately 2.828, and the distance between 1, 1, and 2, 2 is again 1.414. Among these, the smallest distance is 1.414. Thus, the output for this example is 1.414. Now, let's look at a slightly more complex example with 6 points, 0, 0, 1, 1, 3, 4, 6, 1, 7, 2, and 8, 8. We start by sorting the points by their x-coordinates, resulting in the order 0, 0, 1, 1, 3, 4, 6, 1, 7, 2, and 8, 8. Next, we call closest_pair with the indices spanning all 6 points. In the divide step, we split the points at the midpoint, which is the point at index 3, 6, 1. This separates the points into a left half containing 0, 0, 1, 1, and 3, 4, and a right half containing 6, 1, 7, 2, and 8, 8. For the left half, since it contains only 3 points, we calculate all pairwise distances directly. The smallest distance is 1.414 between 0, 0, and 1, 1. Similarly, for the right half, the smallest distance is also 1.414 between 6, 1, and 7, 2. In the combined step, we compare this minimum distance of 1.414 across both halves and check the strip around the midpoint for any closer pairs. Since no pairs in the strip have a distance less than 1.414, the final minimum distance remains 1.414. Finally, consider an edge case where some of the points overlap. The input points are 0, 0, 1, 1, and 0, 0. After sorting by x-coordinates, the order becomes 0, 0, 0, 0, and 1, 1. With only 3 points, we use the base case to calculate the distances directly. The distance between 0, 0, and 0, 0 is 0 since they are the same point. The distance between 0, 0, and 1, 1 is 1.414. The distance between the second occurrence of 0, 0, and 1, 1 is also 1.414. The smallest distance in this case is 0, which occurs due to the overlapping points. This example highlights the importance of the base case in handling small subsets and accurately accounting for edge cases. Additionally, sorting ensures the divide and conquer strategy is efficient, while the strip check minimizes unnecessary comparisons. The output for this example is 0. To understand the time complexity of the shortest distance function, we first analyze the sorting step. Since the input points need to be sorted by their x-coordinates, this operation takes n log n time. This is because sorting algorithms like merge sort or quicksort, which are typically used for such tasks, have a time complexity of n log n in their average and worst case scenarios. Sorting is therefore the initial computational cost in our divide and conquer approach. Now, let's break down the divide and conquer approach. The closest underscore pair function splits the points into two halves recursively, which divides the problem into smaller subproblems. The conquer phase involves three key steps. First, constructing the strip of points that fall within a given range takes n time, as every point needs to be scanned. Second, sorting the points in the strip by their y-coordinates may take k log k time, where k is the number of points in the strip. However, since k is proportional to n in the worst case, this step simplifies to n log n. Finally, checking the points in the strip involves comparing each point with the next few points, up to a maximum of 7 comparisons, based on geometric properties. This step is linear in the size of the strip, or k. Since the recursion depth is log n, due to having the problem at each step, the total work at each recursion level is n. When combined across all levels, the divide and conquer process contributes n log n to the overall time complexity. Therefore, both the sorting step and the divide and conquer approach have a time complexity of n log n, making it the overall time complexity of the algorithm. Turning to space complexity, let's consider the different components. First, the sorting step requires n additional memory to store intermediate results during the sorting process. Next, the recursion stack for the divide and conquer approach has a depth of log n, as the problem is split into two halves at each level. Each recursive call requires 1 space for local variables, so the total space used by the recursion stack is log n. Lastly, the strip construction at each level of recursion requires n space in the worst case, as the strip could potentially include all points. However, this strip space is not cumulative across recursive calls. Therefore, while sorting and strip construction each require n memory, the recursion stack adds only log n. The overall space complexity of the algorithm is determined by the most significant factors. Both sorting and strip construction require n memory, which dominates the log n used by the recursion stack. Thus, the total space complexity is n. Comparing this to the brute force approach, we see significant improvements. The brute force approach, which calculates the Euclidean distance between all pairs of points, has a time complexity of n squared. It is computationally expensive for large datasets and may require n squared space to store all pairwise distances. On the other hand, the divide and conquer approach reduces the time complexity to n log n by minimizing unnecessary distance calculations and leveraging geometric properties. The space complexity is also reduced to n, making the algorithm both time and space efficient. Let's now analyze the algorithm under different scenarios. In the best case, the points are well separated, resulting in a strip with minimal work required for comparisons. Despite this, the time complexity remains n log n, due to the sorting and divide and conquer steps. In the worst case, the points are clustered, leading to a larger strip that requires a higher constant factor for comparisons. However, the asymptotic complexity is still n log n, as this step does not fundamentally change the divide and conquer structure. On average, for a random distribution of points, the algorithm performs efficiently with an average complexity of n log n. Mathematically, the big O complexity is derived by observing that at each recursion level, the work done is n, while the recursion depth is log n. Combining these gives t, n, equals o, n log n, which matches the sorting step's complexity. For space, the o, n, strip storage and o, log n, recursion stack dominate, resulting in an overall space complexity of o, n. Now, let's dive into some common mistakes to avoid when solving this type of problem. First, relying on a brute force approach without optimization can be problematic, especially for large inputs. Algorithms with time complexity of O, n squared, or worse are prone to timeouts, so it's important to explore optimized solutions that incorporate data structures or divide and conquer techniques. Secondly, it's easy to overlook edge cases, such as duplicate points, negative coordinates, or scenarios with very few points. These can lead to incorrect results, so thorough testing is crucial. Another frequent issue involves floating point inaccuracies. When using the Euclidean distance formula, precision errors can creep in, making direct comparisons unreliable. Instead, you might consider using integer comparisons to avoid these pitfalls. Additionally, misinterpreting constraints, like ignoring the maximum input size, can result in inefficient solutions in terms of both time and space complexity. Lastly, assuming the problem space is continuous can lead to unnecessary complexity. Some variations may restrict points to a grid or integer coordinates, and failing to account for this can make your solution less efficient. Now let's take a look at some key insights for approaching similar problems in interviews. Recognizing patterns is essential. For instance, many geometric problems can be simplified by reducing dimensions, identifying symmetry, or leveraging sorted data structures. Divide and conquer techniques are particularly effective for distance-based problems, as demonstrated by the closest pair of points algorithm. Additionally, advanced data structures like balanced binary search trees, heaps, or KD trees are often valuable tools for optimizing spatial computations. Keep in mind that interviewers tend to focus on how well you optimize your solution, so it's important to clearly explain your thought process and the trade-offs involved. To practice, you can explore related problems such as closest pair of points, number of boomerangs, maximum number of points on a line, and minimum cost to connect points. These problems share similar themes and can help you build a strong foundation for tackling distance-related challenges. Finally, let's explore some alternative approaches to solving distance problems. Divide and conquer is a highly efficient method for finding the closest pair of points in O, n log n, time. This approach involves splitting the points into halves, solving the problem recursively for each half, and then merging the results. While it's powerful, the trade-off is that the implementation can be more complex compared to simpler methods like brute force. Another approach is sorting the points by one coordinate, such as the x-axis, before running your algorithm. This pre-processing step simplifies pairwise comparisons and can significantly speed up computations, though it introduces an additional O, n log n, overhead. For approximate solutions, a grid-based approximation method can be useful, especially for very large datasets. This involves dividing the space into grids to reduce the number of comparisons needed. The trade-off here is a potential reduction in accuracy, depending on the size of the grids. Each of these approaches has its strengths and weaknesses, so selecting the right one depends on the specific problem constraints and requirements. Great job! Today, we covered problem number 612, shortest distance in a plane, and explored various approaches to solve it. Remember, geometry-based problems are not only common but also fundamental in many technical interviews, so keep practicing. Thank you for watching, and don't forget to subscribe for more problem-solving content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!